in that direction, don't they really isolate themselves from the rest of the industry? And going in a parallel path really keeps them, gives them some real issues with communicating, or with interoperating, I should say, with LTE. Isn't that a problem?
Yeah, in general you are right. But this is what happens. Sprint had some spectrum that they had to use, otherwise they would have lost that. So they looked around, and the only thing they found was WiMAX, because LTE is just being defined, right? We just completed the standard work for most part in late 2008. So they really did not have any choice. Okay, they wanted a better packet data system. Only WiMAX was available, so they picked WiMAX. Now, from the perspective of interworking, even though I agree with you that if they do LTE, right, then it's much better for them, okay, in terms of interworking. Having said that, there is still interworking supported even between LTE and WiMAX. So their WiMAX system and Verizon, AT&T, LTE system, they can still work with each other, and even Sprint can deploy the core network, EPC, Evolved Packet Core Network, and then they can share that core network between existing DO system and the new WiMAX system and so on. So they can reuse the core network even between WiMAX and let's say DO. Okay, and they can have smooth interworking between their WiMAX and other folks' LTE. So they can still do that, and of course they can always do LTE in future. No one prevents them from doing that. So in general, yes, they have sort of this kind of problem. Right? They even had Nextel, and then it didn't go that smooth. But really, they did not have any choice at that time. In future, they can change their mind. They can also do LTE, but in terms of interworking, it will be okay. Not great, but it will still be working.
How about Alcatel-Lucent's competitors? Are they more focused on LTE or WiMAX?
I think more and more folks are going toward LTE. Okay. For example, the big UMTS vendor, right, your competitor Ericsson, they don't care about WiMAX at all. Qualcomm, nothing to do with WiMAX. So most traditional cellular vendors and operators, they are sticking to LTE. So they are putting their weight behind LTE. Okay. But the new entrants, the folks that want to compete with existing operators, they would like to use WiMAX, right, as a way to get into the market. Yeah. So let's say Intel, Cisco, they are new to cellular. Right? They do not have any installed cellular networks. So they are putting their weight behind WiMAX. So Intel, for example, ships the laptops with WiMAX capabilities. Right? So same with Cisco. Right? They want to also benefit from this wireless data. They said, oh, WiMAX is a way for them to enter this new market segment for them. So for new operators and new sort of vendors, WiMAX does make some sense, right? Because they don't need to worry about other stuff, right? But for existing operators and vendors, LTE gives a pretty good confidence. Okay, we have one more question on the questions box. LTE and 2G, would this indicate an AT dual mode? Yeah. So yeah, LTE and 2G would also coexist, correct. So you have interworking between, let's say, GSM voice and LTE. So yes, we will have hybrid devices like that also. So maybe some folks will directly go from 2G to 4G. No need for 3G. Right? So they can have GSM 2G and LTE 4G. Nothing wrong with that. Even now, you will be amazed, but even now, we are shipping GSM base stations. Who would have thought? Right? Because it's very cheap, very cheap. So still GSM is growing. So yeah, so there will be interworking. There will be dual mode devices. Correct. Correct. So very good, very good. Keep the questions coming. Any other questions? So if you prefer audio bridge, here is your chance. So we'll wait for 30 more seconds. If no question for 30 seconds, then we will resume with the presentation. Oh, we have one more question. Okay, is 20 megahertz widely available? Now it depends on the operator. Okay, but my understanding is that at least 10 megahertz is widely available. The 10 megahertz chunk, 10 megahertz uplink, 10 megahertz downlink, that is widely available. Some operators may have 20 megahertz bandwidth, okay, but 10 megahertz is widely available. That is my understanding. But big operators may also have 20 megahertz chunks. Okay, good question. Good question. Any other question? So again, I will start my 30-second timer.
Okay, another question.
Yes?
You indicated that newcomers would go into WiMAX as opposed to going into LTE. What would be the advantage for newcomers as opposed to existing, service providers?
Oh, okay. So what I mean by that is, let's talk about some small operators, okay? Some small new operators, and they want to maybe replace DSL and cable modem. Right? So instead of we using DSL modem, etc., cable modem, they will offer us at a cheap rate this fixed WiMAX type services. And fixed WiMAX you can deploy in unlicensed spectrum, so you do not need to buy any spectrum. Okay, no licensed spectrum is required. So then you can start offering those services very, very quickly. And there are hundreds of companies, very small companies. Some you may never heard of, let's say Pico chipset, Elverion, Capoto Network. We have no idea about these companies. Okay, even those companies are offering chipsets, offering the base station devices. They are offering the mobile devices and the chipsets. Let's say Sequence Semiconductor. So a lot of companies are there. So then you can buy this kind of mobile device and not mobile, but let's say fixed devices, wireless devices, and the base station. You can get it very, very low cost because there is a lot of competition and unlicensed spectrum, right? So anyone can start doing that. So that's sort of the opportunity for those guys. But if you are a big cellular operator, and then of course you have existing customer base, and your customers are used to nice services. Hopefully they have good opinion about you. So since you can better control quality of service, no need to worry about interference too much when you are deploying in licensed spectrum. So for those guys, LTE is probably more logical choice.
Thank you.
Okay, you are most welcome. Any other question? And again, we welcome and we appreciate your question. Any other question? So my timer had just got reset. So again, 30 seconds. I will start now. Okay, very good, very good. But please keep your questions coming through the questions box, okay? So Eric, let's mute the bridge, please.
The conference has been muted.
Okay, so we said that in 3G we have two distinct core networks, circuit and packet. And the air interface, of course, based on CDMA. And when we move to 4G LTE, then instead of CDMA, we'll be using another technique, OFDM, orthogonal frequency division multiple access. We will discuss a lot of details of OFDMA in the next session, session number 2. But basically it is more efficient, quite efficient for data, high-speed data. The radio network is formally called EUTRAN, Evolved Universal Terrestrial Radio Access Network. And of course, you have the acronyms with you inside the PDF file. Okay, so you can look up there. And of course, you can always ask me a question. So that's the Evolved Universal Terrestrial Radio Access Network. There's the radio network. The core network is formally called EPC, Evolved Packet Core. So as you can see, there is only one core network. So no more circuits, only one unified packet switch core network. Together, the radio network and the core network, EUTRAN and EPC, together they constitute so-called EPS, Evolved Packet System. Evolved Packet System is end-to-end. Both the radio and the core are included inside the EPS. This EPC connects to the PSTN so that we can talk to someone who is using a landline phone, or of course we can access the internet and read some news from some web server, let's say CNN.com, something like that. So we have both the capabilities of circuit switch world and the packet switch world, okay, even from the IP-based packet core network. That's the transition. Here are the building blocks of LTE. And for that matter, even WiMAX has the same building block. Air interface. What do we use? We use OFDMA as the multiple access technique. Multiple users are able to access the system at the same time using OFDMA technique. Also, we have available to us various advanced antenna techniques. We mentioned one name, MIMO, multiple input, multiple output. There is just one technique. There are several techniques available to us. So those techniques will make our air interface very efficient. And basically, that is the main factor that helps us get 300 megabits per second type data, very, very high data. Then we have the radio network architecture that is now distributed or flat. Right? So basically, no RNC. The base station is doing the 3G base station work and 3G RNC work, where we have more processing requirements at the base station now. Everything is based on IP. So when we say that two base stations can talk to each other, then they will use IP for communication. So it's fully IP-based radio network. Since there is no RNC, we are able to reduce latency because from the core network, the packet will directly go to the base station. So the packets are now buffered at the base station, at the E node B, rather than at the RNC. And remember, RNC takes care of hundreds of thousands of subscribers. Very, very busy. However, the base station is taking care of fewer devices, so it is not that much busy. Okay, so it can respond to the request very, very quickly. So that is one reason why we have lower latency. That buffering is no longer at the RNC. Of course, since there is no RNC, the backhaul delay between the RNC and base station, that also goes away. Okay, no need to worry about that kind of transport delay. Also, not only that, I mentioned that every 1 millisecond we can change things, right? Every 1 millisecond we can send a packet. So that also one more factor to reduce the overall delay. So in summary, this kind of architecture helps us reduce the delay, and we can make decisions quickly at the base station rather than relying on the RNC, who may be very, very busy. That's the radio network architecture. So we are moving toward the flat distributed architecture. How about the core network? As I mentioned, only IP-based core network, EPC. Right? So the $1 million piece of equipment, MSC, Mobile Switching Center, is gone. History. No circuit switch core network at all. So now we can buy IP-based components for our core network. To offer a variety of services to the user, we can use IMS, IP Multimedia Subsystem. In fact, Verizon Wireless recently awarded Alcatel-Lucent the contract for all the three major pieces. So you got the radio network contract, the EU-TRAN contract, you got the core network contract, and you guys also got the IMS contract. So you can expect good raise this year. Okay, so that's the three components: the radio network, core network, and the services IMS. So you have all the three types of business segments taken care of by Verizon Wireless. Now this IMS, the main idea behind IMS is it's very easy to introduce new services, and you can do that cost effective. So let's say you want to offer voice plus text, voice plus video. You can do that very easily using the help of the IMS network. Only imagination is the limit. Third parties can develop any new applications, and you can incorporate those applications by using application servers. The IMS network will provide you access to various applications. So we don't need to worry about applications. Right? Any new service can be easily offered, and you can do that cost effective. That is another advantage of IMS. Yeah, sorry about this poor resolution. When I write on the live meeting screen, my handwriting is not that good because the resolution is not good. But hopefully you can figure out what I'm writing. So easy to offer new services, and we can do that cost effective. Okay, very good. So I heard that even Nortel is giving out bonuses, and they are bankrupt. And you guys are in business with contracts from Verizon, so you should of course get much better raise compared to Nortel folks. Okay. Okay. So those are the key building blocks of LTE and for that matter, WiMAX call. Now let's take a closer look at those building blocks one by one. But of course, we'll get more details in subsequent sessions of the series. Okay. But here is the view of OFDM: orthogonal frequency division multiple access. So what do we gain by using this kind of tactic? Okay, so one thing is scalable. So the operator could have very little spectrum, as little as 1.4 megahertz. They can deploy LTE. If the rich operator has 20 megahertz spectrum, they can deploy LTE very scalable. So depending on how much spectrum you have, then you will choose certain bandwidth. Okay. So easy to offer LTE based system. You can apply advanced antenna techniques such as MIMO to CDMA or OFDMA, doesn't matter. It will work for both types of multiple access technologies. However, using OFDMA will make it easy to design and optimize MIMO system. Okay, relatively easy. Applying advanced antenna techniques to CDMA is more complex, relatively speaking. You will get benefits for both, but OFDMA is a little bit easier. Then, how do we take care of multipath? Now, different technologies have different ways of dealing with the multipath. In CDMA-based systems, we use a special type of receiver. The name starts with R, and that receiver will help us with the multipath problem. Who will give me the name of the type of receiver in CDMA? Starts with R, the type of CDMA receiver. Rake receiver. Very good. Excellent. Thank you for your answer. Okay, rake receiver. Now, this rake receiver basically has this kind of rake fingers, So one finger will look at one path, another finger will look at another path. Right? So when our base station is sending out information, maybe we got one direct path, one path got reflected from some sort of building. So now we have two paths. So one path looked at by one finger, another path processed by another finger. So in CDMA, we do not fight multipath. We welcome them because we can combine energies of those multipaths to get even better received signal. Having said that, there is no rake receiver in OFDM system. So no rake in OFDM. So we need to find some other solution to this multipath problem. In the next session, session number 2, we will discuss that, but there is something called cyclic prefix, cyclic extension, and that will help us solve the multipath problem. So even when multipaths are present, we will get pretty good performance. OFDMA is a multi-carrier technology. So let's say I have some spectrum, maybe 10 megahertz bandwidth. I will divide that into many radio channels, tiny radio channels. Channel number 1, channel number 2, channel number 3, and so on. Each tiny channel is formally called subcarrier. So basically, we have divided our spectrum into hundreds of such subcarriers, and we will give the user some subcarriers. So maybe this base station has allocated this user a dozen subcarriers, 12 subcarriers. Another user, maybe we give that user 96 subcarriers, and so on. So basically, we are allocating different numbers of subcarriers to different users. So that's how we share the resources. So resources in OFDMA systems are these tiny channels called subcarriers. One user, one set of subcarriers, another user, another set of subcarriers. And then from one time interval to the next time interval, from 1 millisecond interval to another 1 millisecond interval, we can change things around. So maybe I will give all the 600 subcarriers to one user during tiny 1 millisecond interval. And after some time, maybe I will give that user only a dozen subcarriers. So we can keep changing things every millisecond in LTE, very fast. So that's why we say that, oh, it's a multi-carrier technology, because every user could get multiple subcarriers rather than just one radio channel. We have a question. What is the substitute for rake receiver in LTE? Oh, okay. So this is what we have. So in LTE, there is no rake receiver. So we have a solution called cyclic prefix. Okay, cyclic prefix, also called cyclic extension. That is the solution to the multipath problem in LTE. So no rake receiver, but cyclic prefix. And of course, anytime my answer is not adequate, you want more details, you want better explanation, just submit a follow-up question. If I do not see a follow-up question, then I would assume that you got your answer. Okay. We have some question or comment. Technology is, yeah, correct. So you are right. So we are going back to frequency domain. Yeah, it doesn't sound that appealing once we know CDMA, but this orthogonality piece, as you get correct, is the key. So because of that orthogonality, that's what will make it better than CDMA. So that is correct. Your guess is correct. Orthogonality is the key. So just like we have orthogonal Walsh cores, OVSF cores, just like that we have orthogonal subcarriers. there is no interference among all these hundreds of subcarriers. So we do not need to worry about that. And that's what makes it very, very efficient. Okay, thanks for your comment. Okay, moving forward. Another key building block is advanced antenna technique. Oh, orthogonality. Okay, so we want to get more explanation for orthogonality. Of course, we will discuss this quite a bit in the next session, but let me just give you the basic idea here, okay? Because someone wants more details. So let's say I have 10 megahertz spectrum. This is my frequency. Okay, so I have divided that into several tiny channels called subcarriers. So if I have 10 megahertz spectrum, I would have 600 total subcarriers. Okay, now all those subcarriers are orthogonal to one another. So meaning no interference among these. So in that case, if I have two users, one user, let's say I give subcarriers F1 through F12, a dozen subcarriers. Another user, I give subcarriers F13 to F36, let's say. Now, we have given different sets of subcarriers to different users 1 and 2. Since the subcarriers are orthogonal, there is no interference between two users. Because of orthogonality of the subcarriers. Okay, that is the idea. If you want even more detail, just let me know. Okay, so that is the basic idea. No interference among those subcarriers. There is a special way of constructing those orthogonal subcarriers, and we'll take a look at that in the next session number 2. Okay, and thank you for your questions. So one building block for our LTE was OFDMA. Another building block is availability of these several advanced antenna techniques. Now, one example of multiple antenna techniques is MIMO. We have mentioned that. Multiple input, multiple output. And I will just mention a couple of other names. We have diversity technique, transmit diversity technique. We have something like beamforming technique, where we focus energy in a given direction. So those are some of the techniques that we support in LTE. On this slide, we are giving you potential benefits of using advanced antenna technique. Not all these benefits will be obtained by using just one antenna technique. Some techniques will give you one set of benefits, other techniques will give you another set of benefits. But here we are just mentioning all the potential benefits that we may have. Okay, for example, if you're doing beamforming technique, then maybe the power consumption will go down because you are focusing energy in a given direction. So the transmitter doesn't need to send out that much transmit power. That's the benefit there. If you're using MIMO type technique, then your capacity, your throughput will go up. Okay. So in fact, when you want to get 300 megabits per second, you have to use MIMO technique. Otherwise, you cannot get 300 megabits per second. So if your goal is to increase the throughput or increase the number of users significantly, then you need to have some sort of MIMO type technique. Improved spectral efficiency, bits per second per hertz. So beamforming, MIMO technique, they will help you increase the efficiency. Beamforming is also helping you reduce interference because your energy no longer goes all over the cell, all over the sector. We are sending beam in a specific direction. So you are potentially reducing the interference. When you do beamforming or if you do diversity type technique, then you will be able to increase the cell radius. Okay, so cell size can be larger. Overall signal quality also will be better if you do beamforming or diversity technique. So in summary, there are several benefits of using advanced antenna technique. As they say, there is no free lunch, and they are right. What is the cost? Well, the complexity. Right? The complexity of the system goes up. But that's the way it is. We have to use those advanced antenna techniques to get superior performance that LTE promises. Okay. We will indeed use advanced antenna techniques, even from the day one in case of LTE. Now we have got several questions, so let's answer those. Okay, so different frequencies, not the slot. Yeah, so in general, within a time slot, let's say I have 1 millisecond time slot. So within that 1 millisecond time slot, I can support different users using different subcarriers. Okay, yeah, so orthogonality can be obtained in that frequency domain during the same time slot. That is correct. And by the way, you can look at all the questions in the questions box. Okay. Okay. Another question from mobile point of view. Will all support 20 megahertz or some may support? Okay. Now, from the perspective of the standard, yeah, all the terminals can support 20 megahertz bandwidth. There are some other features such as the number of antennas and so on, modulation scheme, for example. Those things could be different, but as far as I understand, all the users can support 20 megahertz bandwidth because we will have the baseband chipset that will have the capability of supporting that. So, for example, we would have so-called 2048.FFT. So that kind of processor is already available in the chipset. So it is capable of supporting up to 20, but we can use in a given area maybe 10 megahertz or 20 or 5 megahertz. So that is up to the operator. That's how much bandwidth to use. But from the perspective of the device and the base station, we will have the capability of 20 megahertz. Okay. Yeah, and different operators may have different amounts of spectrum bandwidth, so that is okay. That is okay. Can antenna and by the way, when the terminal looks at the broadcast channel in a given cell, it will know whether that cell is using 10 megahertz or 20 megahertz or 5 megahertz, whatever bandwidth is being used. So if you go from one operator to another, maybe one operator is using 10 megahertz, another reach operator maybe 20 megahertz, it is okay because we will know the change in the bandwidth when we look at the broadcast channel. So no problem, that is supported. And can antenna techniques be dynamic depending on the changing system load? Yes. These techniques are dynamic. So maybe during some time period, you are using MIMO technique, but after some time, the channel conditions are such that you can no longer support MIMO. Then you can go back to diversity technique. So yes, it is dynamically determined. That is correct. So you are not stuck to some technique forever. Okay, you can dynamically change. And here U is the base station scheduler. E node B scheduler is in charge. So it will determine what technique to use, what kind of data rate, what kind of modulation scheme, who should get data, and so on. So the scheduler is very, very powerful in LTE, and the E node B scheduler has a lot of control. Okay, very good. Thanks for your question. Keep the questions coming. Okay. we covered all the things here. Very good. Let's move forward. Another building block is the core network, and we will have all IP-based packet switch core network. And here we are showing the core network connected to the LTE radio access network EUTRAN, and decentralized architecture, flat architecture will help us reduce the latency. But you can connect this to any other technology. You can connect it to an XCVTO, WiMAX, UMTS, or whatever. Doesn't matter. Okay. And this will be your common core network. So this is the step in the direction of IP convergence. We are converging in the network from the architecture perspective. Okay. So that's the idea. Several new components you will observe, and we will discuss those in this session itself a little later. MME, SGW, PGW, those are the main components of the core network. Then we have IMS, IP multimedia subsystem, and for those we have components such as call session control function, media gateway, etc. IMS has access to various application servers. So maybe one application server takes care of location-based services, another takes care of video streaming, and so on. So we can offer a variety of services to the user. Okay, so that is the overall idea. Then you will see some traditional components also, domain name system, DSCP, etc. But from the pure LTE perspective, PGW, MME, SGW, those are the main components of the core network. Here is a question for you. So please provide me your answer. I will give you a couple of minutes to think about it. And in the meantime, we have this question here. Major LTE chipset manufacturers. Major LTE chipset. So I believe, for example, Qualcomm will be the main manufacturer for chipset, and these infrastructure vendors, right? They would have probably their own solution, maybe ASIC or DSP or something like that. So Ericsson may have some solution, right? Alcatel-Lucent, I do not know personally, but maybe you have some OEM arrangements, or maybe you have your own chipset. I am not aware of that yet. But major vendors from the infrastructure perspective, you may have that chip, you may have your own chipset, but at least Qualcomm will give you the chipset. Okay. So in my opinion, Qualcomm would be still the main, major chipset manufacturer for both the base station and the device. But major infrastructure vendors may have their own solution. Some work with companies such as Texas Instruments to develop the chipset or the DSP-based solution. So, for example, for WiMAX, some vendors have used TI, Texas Instruments. Okay. Okay. So 100% accuracy. Very good. Very good. No core network. Okay. No core network in the no circuit switch core network in the 4G setup. One more question. I'll give you a minute or so. Okay, we have a question. What timing system is used in LTE? Okay, a very good question. Now, if you look at the standard doesn't say what to do regarding timing mechanism. So if you want, you can use GPS. Standard doesn't prohibit you from using GPS. However, if you're deploying FDD frequency division duplexing, the use of GPS is not mandatory, not actually required. So you can have your own mechanism, okay, to support timing. So there is no standardized way of doing that. Okay. But let's say Verizon deploys this, then probably they will use GPS. Okay, it makes sense because they already have that today. So why not? But as far as the standard is concerned, there is no requirement or no specific recommendation. So you could use GPS, okay, just like CDMA, but it's not required. Good question. Good question. Okay, so we have 95% accuracy. Very good. So UMTS LTE. So it is a release 8 feature. Release 8. Okay. So let's move forward. Okay. So architecture. That's our next major topic of discussion. In 3G systems, we have the base stations or node B controlled by a radio network controller. The RNC connects to the circuit switch core network, let's say MSC, so that we can access PSTN, and it connects to the packet switch core network. In case of DO, we have components such as PDS and foreign agent and home agent. And in case of UMTS, we have SDSN and GGS. And the packet switch core network, of course, helps us access the internet. So that's what we have in 3G. Now moving to LTE based for this system, the radio network, which we formally call EU-TRAN, nothing but the base stations E node B, evolved node B, that is our base station. And now you will see something you have never seen before. 2 base stations can now talk directly. In 3G systems, 2 base stations can never talk to each other, right? Because they are all controlled by the RNC. However, in LTE, we have these interface, so-called X2, between 2 base stations. So that will help us communicate between 2 base stations. That is new in 4G, new interface. The base station E node B connects to the core network. Okay. And the core network EPC can interface with PSTN, it can interface with the internet. So now we'll take a look at the radio network and the core network in more detail. Oh, we have a question here on release 9. Oh yeah, so release 9 will probably include some enhancements to the basic LTE. But it's not yet finalized, right? So it will take some time because it's just like work in progress. So yeah, we believe that there will be some enhancements to LTE. Now there is so-called LTE Advanced, and as part of LTE Advanced, we have to do some additional features because the ITU is soliciting proposals for formal 4G systems. Okay. So LTE will be submitted as one of the 4G proposals. So if you want to formally qualify as a 4G system, you need to support 1 gigabit per second. 1 gigabit per second data rate in fixed environment or mobility environment. So I suspect that maybe we will have certain LTE advanced features being incorporated as part of Release 9. Release 9 also has probably some enhancements to the basic HSPA plus that we have done in release 7 and release 8. So there are some features that would be HSPA plus feature, but from the LTE perspective, yes, there will be some enhancement in release 9. X2, is it point-to-point or point-to-multipoint? Yeah, so X2 is a logical interface between two E-node base. So yeah, so it is a point-to-point between two E-node base. So yeah, it is a logical point-to-point interface. That is correct. So, okay, very good. Let's start looking at the core network and then the radio and the core more closely. From the radio network's perspective, this is what we have. Nothing but the base station. One base station, another base station, another base station. And the base station in a given neighborhood can communicate among themselves through these X2 interface. Now, X2 interface is a logical interface. Okay. So logically, these base station 1 and base station 2 can talk to each other. In practice, there will be some sort of private IP network. There will be some sort of router, and that router will get packet from one base station, and it will forward that packet to another base station. So in terms of physical implementation, there will be some private IP network owned by that service operator. But logically, we have communication between two base stations via X2 interface. We have highlighted several times that in the radio network there is no RNC. So whatever RNC is doing in 3G, let's say handover algorithm, for example, power control algorithm, some aspects of that are in the RNC. Now those things are now done by the E-node base because there is no RNC. The X2 interface is primarily to support mobility or handoff. Handoff, handover, same thing, but handover is a formal term used in LTE. So whenever UE goes from one base station area to another base station area, then the two E-node Bs will communicate via this X2 interface and say, this will ask, let's say here is the source, here is the target. So the source will ask them, okay, do you have adequate resource to support the handover? The base station 2 says, yes, I have. So it means that we will have successful handover from base station 1 to base station 2. So this kind of interface helps us with the handover signaling between two base stations. So that is one of the main functions of X2. Okay. Not only that, we have connectivity between the base station and the core network. Now, for our discussion here, let's say this is MME1, MME2. And one question we have here, is a soft handoff applicable in LTE? No, there is no soft or softer handover in LTE. The only thing we have is hard handover. So at a given time, our mobile device communicates with only one cell or sector, only one cell. So as we go from one cell to another, one sector to another, one base station to another base station, we will be doing hard handover. But do not worry too much about the word hard, because it will be quite fast. So from the user experience perspective, we should not have problem with user perceived experience, because we'll be able to do the handover quickly. Yeah, so in summary, hard handover, not soft or softer in LTE. WiMAX, same idea, hard handover. And then, how many other cells can a cell talk to using X2 interface? Personally, I have not seen any limit, but normally, this is, as I mentioned, right? This is like some private IP network. So I would guess, I mean, in general, one eNode B, in general, will talk to maybe up to 6 eNode Bs, and then you have covered the entire geography, right? If this is the cell, let's say base station 1, then who are in the immediate neighborhood, right? So in this case, let's say 6. So in general, you would have this kind of connectivity, right, between one base station here and the neighboring, let's say 6 base stations. So in general, 6 should be more than good enough. However, in terms of this IP connectivity, we could have hundreds of base stations in one neighborhood. So let's say pick one big city, right? And inside that city we have this IP network, and then all the base stations inside that city, hundreds of them, connect to the IP network. This MME core network also connects to the IP network. So in general, they are capable of exchanging information with hundreds of base stations, but for handover signaling and so on, based on the geography, maybe 6 is more than good enough. So hopefully that gives you enough information. Okay. And X2 is a logical interface, right? Logical. So the router here in the IP network, this is an IP router. It will just forward the packet from one base station to another. So theoretically, one base station can send packets to maybe hundreds of other eNode Bs in that city, but practically it may not be required. Okay, and then we have some other clarification. X2 can be implemented. Okay. So we have some information for the folks here. Can be implemented using SDW as a gateway to avoid point-to-point BTS interface. I see. So in terms of physical implementation, here one student is mentioning that we have this serving gateway. So we can route the packet through this path in terms of physical implementation. So it may be, you can design that way if you wish. After all, it's an IP network, right? And it is up to the service operator how it wants to physically implement this kind of connectivity. Okay. But so I'm not saying that we have this kind of point-to-point physical link running, right? We have this base station, let's say, connecting to some this router, right? IP network. Another base station has a gateway that connects to the IP network. So we do not really need to have just T1 link or some optical fiber running between two eNode Bs directly. All of them connect to this kind of IP network, and this backhaul network can use optical fibers or whatever, microwave, whatever we want, Ethernet, for example. You can use any of such mechanisms to have logical X2 implemented. Okay. Thank you for your questions, and thank you for providing the information on using SDW as a gateway. Okay. Very good. Keep the questions coming. Okay, where were we? Yes, so we were discussing this kind of architecture and X2 primarily to support mobility. But between two eNode Bs, we have X2 interface. Okay, and then between the and we are discussing this aspect. Okay, so let's say two MME, mobility management entity. So now one base station here, eNode B1, is connected to two MME, and that is the S1 interface. between the radio and the core network, the interface is called S1. And specifically, if we are talking between E node B and MME1, it is called S1 MME interface, if you want to be more specific. So S1 MME is that interface between E node B and the MME. Now you will observe that we have multiple connections between the base station and 2 MME. Can you think of any use of such multiple connectivity? So one base station connected to two sort of core network entities. What may be the benefit of connecting to 2 MME rather than just one core network element? What kind of benefit we could possibly derive? Okay, so one has a redundancy, fault tolerance. Okay. So that is load balancing, IU flex. Yeah, very good, very good. So in basic UMTS, we have so-called IU flex. Okay, so basically our radio network can connect to multiple core network element. Okay. And actually it's many-to-many interface. But let's take this example. Similarly, here we have so-called S1 flex, flexible. So, couple of reasons. So some of you mentioned redundancy, fault tolerance. So that could be done. But more specifically in LTE, we have load balancing possible between 2 MME. So it, based on the situation in these 2 MMEs, we would choose for a new call maybe MME1, maybe that is lightly loaded, maybe more capacity is available in MME1, then we will choose MME1 so that we can balance the load across MME. So there is one sort of so redundancy, of course, you can always do that. Fault tolerance, so that is of course valid. Fault tolerance. Then we have load balancing. Then we have network sharing. Okay. So let's say Verizon Wireless has deployed this EU file. Okay, let's start from there. Okay, so this is all Verizon Wireless. And this is Verizon core network. Now, we have Disney Mobile. So Disney says that, okay, I want to offer services. So we have this Disney subscriber who gets, let's say, Disney movies, cartoons, etc. So they have business relationship with Disney Mobile. Now Disney does not need to deploy the base station. So they say, okay, we will have some sort of agreement with Verizon Wireless. Okay, and based on that agreement, we will allow the Disney Mobile to access the Verizon network. So in this case, we are sharing the same radio network between two operators, two service providers. Okay, so this multiple connectivity with these MMEs, these core networks will help us implement that kind of functionality. So those are some of the ways in which we can exploit the connectivity between one E node B and multiple MMEs. So, what kind of functions are performed by the base station? Since there is no RNC, that all the functions need to be done by the base station. So our E node B takes care of the radio resource management. Okay. For example, maybe we'll give X number of subcarriers to one user equipment 1, then we will give another set of subcarriers to another user, and so on. So the base station scheduling algorithm will do that. Okay. Then we have header compression. Now there is one more interesting piece of information. In LTE, the base station has full visibility of this IP packet, pure IP packet. See, in 3G, our base station never sees a pure IP packet because the RNC already breaks the IP packet into some segments, radio link protocol, radio link control, RLC, RLP segments. So the base station doesn't see the full-fledged IP packet. However, in LTE, from the core network, from this SGW, the IP packet would arrive at the base station. So that IP packet has a header and then the payload. The header would have source IP address, destination IP address, etc., etc. So now the base station can actually see the full-fledged IP packet, and then it can take care of header compression. The base station also can do encryption. It can send broadcast information. It can send a page to the user using their interface. Handover is also done by the eNode B. And as part of the call setup, it will pick the specific MME for that user at that time. Those are various functions performed by the eNode B, our base station. Okay, now let's turn our attention to the core network. As I mentioned earlier, in the core network, the main entities MME, SGW, PGW. Okay. So, okay, and we have this HSS. So let's take care of HSS first. Home subscriber server. Hopefully, the acronym list that you have has the full name, Home Subscriber Server. So think of that like your HLR, Home Location Register. It has basically subscriber database. So we would say that, this user is maybe platinum type subscriber, maybe here is the secret code for the user, secret key that we will use for authentication and so on. So it's a database for all the subscribers. We will also store the location of the user, where the user is. User is in Chicago, New York, Dallas, wherever. So this is your subscriber database, HSS. So HSS is formally part of the core network. Okay, then mobility management entity. Some of the functions are authentication. So during the call setup, MME will work with HSS to authenticate the user, to make sure that the user is valid. That's one important function of MME, authentication. Also, paging. So MME will know where the user is. Okay. So based on the location of the user, it will send a page message to all the eNode Bs in that area. So whatever we call location area, paging zone, etc., that is now called tracking area in LTE. Tracking area. So we will know as an MME that, this user is in tracking area number, let's say, 50. So all the eNode Bs in that tracking area 50 will get a page message from the MME. And then they will send that page over the air. Since we are here, then we will respond to the page message. So that is the idea. So these are some of the functions that MME takes care of. Call setup signaling is responsible of the MME, and as part of that we do this authentication. So that's what MME does. One thing that we should keep in mind, that MME takes care of only signaling. Only signaling. No traffic. User traffic does not pass through MM. So just keep that in mind. MME is only for the signaling purpose, not for traffic. Traffic does not pass through the MM. Okay. SGW. This is where the user traffic is passing through. You can think of SGW as a router. So for example, let's say we are somewhere here and we are reading news from CNN.com. So the CNN homepage will come in the form of IP packets. It will pass to the router. It will come to the PGW. From PGW, it will go to the SGW. From SGW, it will go to this base station here, and from base station to the user equipment. As you can see, the SGW knows that this specific UE, let's say UE number 20, is taken care of by base station number 1. It has the database that has this UE ID and identity of the base station that is responsible for that user. So we said, okay, user number 20 taken care of by base station number 1. Let's say after some time we move to another base station number 3. So our SGW has this database. So it will say, okay, let me update my database. Base station 3 is now responsible. So whenever a packet comes for that user, now it will be sent to the base station number 3 because that's where the user is. So in summary, SGW is taking care of user traffic. It is forwarding the packet between the radio network and the PGW. So uplink or downlink doesn't matter. SGW is routing the packet. So that is the main function of the serving gateway. It keeps track of where the user is in terms of traffic so that it can forward the packet. So that's traffic router. Another entity is PGW, PDN gateway. Oh, SGW is serving gateway. Serving the gateway. And PGW, PDN gateway. PDN is your packet data network. Internet is an example of a packet data network. Okay, so PGW, think of that as your home agent of my next video. Think of PGW as a GGSM in case of a UMTS type set. So, what does a home agent or GGSM do as part of the call setup? Do you remember? It allocates something to the mobile device. What do HA and GGSM allocate to the mobile device? Some sort of IP address. Very good. Very good. Thank you for the answer. So as part of the call setup, we allocate IP address to the user. So home agent, if you're using mobile IP in 1x video or 1x, then home agent allocates this dynamic IP address to the user. In case of UMTS, GGSM allocates IP address to the user as part of PDP context application. The same way, as part of the call setup, our PGW will allocate IP address to the user. Very, very important function. That is the main function, IP address allocation to the user. And PGW acts like a gateway to the outside world. The packets to the UE, packets from the UE, they always travel through the gateway. So in the downlink or forward link from the outside world, packets will arrive at the PGW. PGW has a database that, okay, for user number 20. Who is taking care of that? Okay, SDW number 5. SDW number 5. So it will forward the packet to this SDW because it is connected to many SDW, to SDW3, etc., etc. So based on the user identity, it will forward that to suitable SDW. SDW will send it to base station and then to the UE. So from the outside world, packet will always arrive at the PGW. So the outside world doesn't need to know where you are. You may be in Chicago, Washington, D.C., San Diego, Los Angeles, doesn't matter. PGW will always know that, oh, I need to forward the packet to the serving gateway in San Diego. So then the San Diego serving gateway will forward the packet to the correct base station in San Diego and so on. If you are in Washington, D.C., then the PGW will forward the packet to the serving gateway in Washington, D.C., and then the base station in Washington, D.C. will get the packet. Eventually, we will send it to the user equipment. So, from the perspective of the outside world, PGW is the gateway, right? Packets always arrive at the PGW. Packets of the UE, they will leave the UE, leave the core network from PGW. The PGW is your anchor. That's your gateway to the outside world. Okay. One more thing I would like to mention here. Let's say I want to connect my 1X video to the LTE core network, EPC. So then you will have your PDSN. Now we have started using evolved core network, and as part of that, we also call HRPD serving gateway. So it is like your PDSN. So this HRPD serving gateway or PDSN, it connects to the PGW. So this guy acts like your home agent. PDSN home HRPD serving gateway is like your foreign agent. So now we have this connection between the PGW and the HRPD serving gateway. So when the packets come from the outside world, they will arrive at PGW. And if we are in the DO coverage area, then from PGW, it will go to the PVSN or SDW. From there to the RNC, RNC to the base station to the mobile device access. So we can use the connectivity between PGW and this PDSN or HRPD serving gateway so that we can have communication with the device in the DO coverage area. The PGW acts like an anchor as far as the user plane is concerned for interworking with 1X video type systems. Okay, one more gateway, evolved packet data gateway. Evolved packet data gateway. Now, how do we use that? Whenever you want to connect an untrusted network to the core network, you have to pass through the EP region. Basically, this is giving us security. So as an example, let's say we have this hybrid device that supports LTE and wireless LAN. So in our home, let's say we are using wireless LAN. Okay. So wireless LAN is considered an untrusted network because you never know. We may or may not have turned on encryption. So even our neighbors can access our wireless LAN. So we never know about that. So we said, okay, let's treat wireless LAN as an untrusted network. So the packets from there will pass through this EPDG, so that we can now have some sort of secure tunnel, and we can make sure that everything that is coming is secure, so we can authenticate and we can do encryption and things like that using the tunnel. So basically EPDG makes sure that whatever enters the EPC and whatever we send to the PGW, right, that is always secure, because we do not want some rogue elements to mess up our core network. Okay. So that's the main purpose. So basically it provides security. Time for me to ask you a question. So please spend few moments. Now, which of these is not considered part of the core network? So remember, we have the radio network and the core network. Radio network is EUTRAN and the core network is EPC. So what is not in the core network? That is the question. What is not in the core network? So I will give you maybe 1 more minute. And please participate in the poll. So the raise that you will get will be a function of how much participation you have in the session. Oh no, just kidding. But please participate. We have, let's see, we have 34 participants, and only 25 are answering. The others are on vacation. So please come back from your vacation and submit your answer. Okay, in the meantime, we will answer this question. Okay, is the tunnel from an untrusted network a standardized protocol? Yes. I think it is IPsec, IP security. So yes, I think we are using IETF based protocol. Yes, standardized protocol. Yes, correct. Please participate. Okay, 10 seconds remaining. Okay, so let's share with you the results. Okay, 92% correct answer. Very good. Okay, E node B is part of the radio network, EUTRAN. So remember, we have the radio network and the core network, and E node B is part of the EUTRAN, part of the radio network. Everything else you see here is part of the core network. Okay. Very good. Okay, perfect time for a short break. So let's have a 10-minute break, and once we come back, we will give you one more opportunity to ask questions using the audio bridge.